All right, welcome back. We are in 4.6 today. We're skipping well, most of 4, but let's get my whiteboard up here and dive into it. So 4.6 is, there we go. Oh, just kidding, there we go. 4.6 is polynomial inequalities and rational inequalities. That's what we're walking into here. Right. So a polynomial inequality is just an inequality that has a polynomial. So for example, something like x squared plus 1 is greater than 0, right? And so we have to figure out ranges of values where this is true. Right? And we can figure out, in fact, let me change this up just to make it a little more interesting. Let's go x squared minus 1 equals greater than 0. Because graphically, if I look at what's happening here, I know what x squared minus 1 looks like. That's just a parabola that goes through -1 and up like that, right? And so the question is where is this function greater than 0? Well, here's 0, right? That x-axis is 0. And so it's greater than 0 there and there. It's strictly greater than 0 if I were to put an open circle right here at 0 and an open circle right here at 0, right? That's where it's greater than 0. And I happen to know that this happens at -1 and this happens at +1. So it's greater than 0 on these two separate intervals. That's all of these x values here and all of these x values here. So where is the solution? What x values gives you x squared minus 1 is greater than 0? Is from -infinity up to, but not including what, -1, unioned with 1, not including, up to infinity, right? Because on these values, way up there, there's positive values on the function. And it's not obviously solved on these 0 values here or in the little part that goes below 0, right? That's not part of the solutions to the inequality. So that's the idea of this chapter. And we're going to talk about how to solve these. So let's dive into one, and we'll do it without graphics. Let me just clear that out. I thought I did already. There we go. So let's take a look at one. Let's look at let's do x squared minus 4x minus 5 is less than 0. Well, on the left-hand side, I can graph this, or I can factor this, excuse me. This factors down to x minus 5 times x plus 1. Right? And the reason I care about that is because I can set this equal to 0, right? I can, off to the side, ask myself what happens when x minus 5 times x plus 1 is equal to 0, right? So we're just interested in that because that'll find us the zeros of this function, right? So I know that either x minus 5 is 0 or x plus 1 is 0. And therefore, if I add 5, right? So kind of in my mind, I'm building the graph, but I don't have to do the graph. I'm going to do the graph for maybe one or two of these, and then we're just going to bail out and not look at the graphs anymore. We'll come back and forth. So, but I know that at 5, I get a 0, right? And I also know at -1, I get a 0. But again, picturing this graph in my mind, it is this function itself on the left here is a positive coefficient. It's a 1 in front. It's an x squared. So I know my end behavior does something like this. And therefore, I really know what the graph does. I don't know how far down it goes, but I don't care. The only thing I'm interested in is when is this graph less than 0? And that happens in that area down there. Those numbers between -1 and +5, not including, because it's a strict inequality. And I'm done. It's between -1 and 5, not inclusive. Bam, that's it. So those ones are fairly easy as long as you know what the graphs look like, right? So let's take a look maybe at this one. Here I have x squared plus 3x minus 5. And I'm going to go greater than or equal to x plus 3. Okay. Now, I don't have a 0 over on the right-hand side, and it was very convenient to compare my left-hand side to 0. So I'm going to get that 0 there. I'm just going to shove everything off to the left-hand side. So I'm going to say minus x minus 3 from both sides. That way, on the right-hand side, I have a 0. On the left-hand side, I get x squared plus 2x, and then minus 8. Excuse me. And I can factor the left-hand side to x minus 2 and x plus 4. And through that same process above, we're going to find that we have zeros at 2 and at -4. Okay. It should be clear where those came from by now. And so once again, graphically, I'm just looking at this 2 and this -4 as being my zeros of the function, right? And this is a positive x squared, so it's going to come down like this and do something like that again. So where is it greater than 0? Well, it's on here and here. I missed a little bit, but that's from these go on forever in the negative direction. These go on forever in the positive direction. So that's -infinity up to -4, inclusive, because it's a inclusive inequality, and then unioned with including 2 up to infinity. And there's my interval. Good. Okay. So it might get a little bit harder as things get harder to see how to factor, or you get higher degree polynomials. So let's solve this one. If I have x to the third minus x, let's say, is greater than or equal to 0. I can factor an x out of this. That gives me x times x squared minus 1. But x squared minus 1 is x plus 1 times x minus 1. So this is x times x plus 1, x minus 1. Where is that greater than or equal to 0? And so I should be able to see that I get 3 zeros. From my x, I get a 0. For my x plus 1, I get -1. And for my x minus 1, I get +1. Okay. Now, without plotting this on a graph, I mean, I'm going to show you kind of two ways. I'll just plot it on the graph. I've got my zeros here at 0. I've got one at -1, and I've got one at +1. I know because this is a positive coefficient and an x third, my end behavior is this. And since each of these are a multiplicity of 1, right? The x appears once, the x plus 1 is once, the x minus 1 appears once. They have multiplicity of 1, so they're going to cross through at those zeros. And look, that looks terrible, but that's what they look like. Where is this greater than 0? Well, here, and then here forever onward, right? So that is, this one happened at -1, this one happened at 0, and this one happened at 1. So that's between -1 and 0, inclusive because of the inclusive inequality, and then union that with 1 to infinity. That's it. The other method is to kind of just think about a number line. And if I have a number line, my zeros happened at -1, 0, and 1. And if these are my zeros, since it's a polynomial, in between each of these zeros, it's going to be continuous. There's no cusps, there's no holes, there's no jumps. So if it's positive at one of these values, it's going to be positive in that entire region. Right? If it's negative, between 0 and 1 is negative. So if it's negative through that entire region. And then once again, if it's positive through that entire region forever. And this guy is negative, therefore it is negative in that region forever, right? So if I can put my zeros in spots, all I have to do is test numbers in between them, right? So let's take a look at doing that without having to draw out the entire graph. If I have a bunch of, and I'll give you something already factored here, but if I have something like x plus 2 times x minus 5 times x plus 7 times x minus 12 times x plus 25, where is that less than or equal to 0, right? Well, drawing out my number line, that doesn't have to be terribly accurate, right? You don't have to count all the spots exactly. I know I'm going to have zeros at -2, at +5, at -7, at +12, and at -25. So at -25, I split my number line. At -7, I split it again. At -2, it gets split, and then at 5, and then at 12, right? I don't care that these are not equally spaced apart. All I care is that I have these regions. And then I'm just going to start testing numbers. So I'm going to test a number in this region, like say -30. It doesn't matter what number, just something that's not -25, but to the left of it. So if I plug in -30, and again, I'm looking for whether this is positive or negative, and that's all I care about. So if I plug it in, I can go -30 plus 2 times -30 minus 5, -30 plus 7, -30 minus 12, and -30 plus 25. I could figure out what these are. -30 plus 2 is -28. -30 minus 5 is -35. But then I'm multiplying these huge numbers, and I don't care. I don't care what the number is. All I care about is it positive or negative. So -30 plus 2 is a negative. -30 minus 5 is negative. -30 plus 7 is negative, right? 23. -30 minus 12 is -42. But I just care that it's negative. -30 plus 25 is negative, right? So I have a negative times a negative, which is positive, times another negative, which goes back negative, back to positive, and back to negative in the end. And so that's all I really care about, is that in this region, it's negative. If I test another number somewhere between -7 and -25, like say -20 is good, I should be able to figure out if this is positive or negative. So I will. -20 plus 2 times -20 minus 5 times negative 20 plus 7 times negative 20 minus 12 times negative 20 plus 25, right? But again, all I care about is the sign. So negative 20 plus 2, that's negative 18. I just care that it's a negative. Negative 20 minus 5, negative 25. It's a negative. Negative, negative, but this one is positive. So I start with negative. When I multiply by the next negative, it goes positive. Multiply by a negative goes negative, and then positive, and a positive times a positive is positive. So all I care about is that in this region, it's positive, right? And you can keep trying numbers. If you try a number between negative 2 and negative 7, like say pick negative 5, you'll see that you flop over to a negative. You're going to flop back over to a positive, and then a negative and a positive. I'll let you go through this and finish this one. But to answer the question then, where is this less than or equal to 0? Well, each of these lines right here is where it is a 0. So there's a 0, there's a 0, there's a 0, right? Where is it less than? Well, it's on all of these negatives, and then we include that 0. So there, there, and there. So my final answer to this question is from negative infinity up to and including negative 25, unioned with negative 7 to negative 2, and unioned with 5 to 12. That is where it's less than or equal to 0. Okay. They have an example here that talks about theorems from 4.4 that we skipped. So I'm going to skip that example because that's not helpful. Let's do this one here. All right, so I'm going to take this one step further and include something that looks like this. 3x over x plus 6 is less than 0. Right? So here I have a couple of issues. If I look at the graph of what this looks like, I might have that graph. It is right here. Yeah, there we go. And so you can see here when if x is equal to negative 6, we have a 0 in our denominator, right? And that is evident right here. It creates a discontinuity. And it happens specifically at zeros of the denominator. And more importantly is that on the left-hand side of that discontinuity, we're positive. And on the right-hand side, in this particular example, we're negative. So over a discontinuity or a 0 of the denominator, we can change the sign. We can go from positive to negative or negative to positive, but it's not necessary that we do. We might not. If it were a second degree or a 0 of multiplicity 2 in the denominator, we might not change signs, right? But the point is that we have to check, right? The other thing is that we have a 0 of the numerator at 0, right? At x equals 0. That's right here. And again, on the left-hand side, I go from negative to positive. Just like on any other 0, I could change signs as I go through or bounce off that 0. So this just tells us that I have to kind of create that same number line, but I want to check. I'm going to divide my number line using zeros of the numerator and zeros of the denominator. And then just check those regions, right? So this one's easy. It's right there. It's graph for us. I don't have to go through and do this. We'll do another one without looking at the graph. So let's do this one. Let's do this one right here. I have x plus 1 over 2x minus 4. And it's less than or equal to 1. So right off the bat, this is not 0. That's not helpful. Well, what I can do is subtract that to the other side, wrap it up into that rational expression, and then have this thing equal to 0. So I'll minus 1, minus 1. This gives me x plus 1 over 2x minus 4 minus 1 is less than or equal to 0. This is what I want. That's good. For this minus 1, I'm going to just call 2x minus 4 over 2x minus 4. Because that's still 1, right? I'm just changing the way that 1 looks. And I can combine these now. And be careful with this minus. That's minus 2x minus 4 and then minus negative 4. So this will be x plus 1 minus 2x, and then minus negative goes to plus 4, all over 2x minus 4. And that is supposed to be less than or equal to 0. So this is negative x plus 5 over 2x minus 4. Less than or equal to 0. I don't know what this looks like, right? But that's okay. My zeros of my numerator I just set that numerator equal to 0. And if I just add x to both sides, I can see that it is 5. Right? And then I want to go through the same process, but define zeros of the denominator. That's just to set the denominator equal to 0. So add 4, divide 2, and I have x equals 2. So I have two zeros. I have the 0 of the numerator, and then I have this, the 0 of the denominator is often called a critical 0. It's not really a 0 of the function, right? So we have to make sure that we note that, because in this equation, or this inequality, we are also interested in values where this is equal to 0, right? And at x equals 2, the function is not equal to 0. It's a critical 0, meaning we're trying to divide by 0. There is no value there, right? So when I make my number line, I'm going to make it with, I'm going to write my 5 here, and I'm going to put a full dot there to indicate that it is a real 0. Because when my numerator is 0, my function is 0, right? But when my denominator is 0, you can use red, you can use whatever you want. It's positive 2, right? Yeah. Then at 2, I'm going to leave an open. I'm going to put it red. I'm not always going to do that, but at 2, and a lot of times I like to just draw a dotted line like this, just to make it blatantly obviously clear that that is not a 0. So whatever you do to make sure that you know that's not a 0, but one of those discontinuity spots, right? And then I just have to check. Is it positive here, negative here, positive here, negative here? Sometimes I'll do a black line here, but I just have to check those 3 lines. or those three intervals, and I'm checking this. Right? I'm just plugging in a number into that to see if it's positive or negative. If whatever I plug into that is less than 0, then it solves it. If it's greater than 0, then it doesn't, right? So I'm going to plug in, let's just grab a value. 0's over here. I'm going to do it in maybe blue. 0's over here. That's going to be one of my numbers I check. So I'm going to plug in 0. That would be -0 plus 5 over 2 times 0 minus 4. But that's just 5 over -4, which is a negative number, right? So in here, I know I'm negative. Check the next number, check some number between 2 and 5. It doesn't matter which number, throw in 3, right? So then I have -3 plus 5 over 2 times -3 minus 4. -3 plus 5 is 2. 2 times -3 is -6. I feel like I messed up. -4 is 2 over -10. Did I mess up somewhere? Not that this helps because y'all aren't watching me do this live. No, I don't think I did. All right. But again, this is negative. That's why I'm wondering, is because over this 2, I should switch. Oh, that's why, because for whatever reason, I decided that when I tested 3, I was going to plug in a negative right there. That doesn't belong. So let me just back this thing up. I'm plugging in 3 into this thing, so it's negative because there's a negative here. 3 plus 5, and then I carried that negative down, but it doesn't belong there. That's a 3. -4, right? And so this is 2 over 6 minus 4, which is 2. It's 1, but I don't care if it's 1 or a million. It's positive. That's what I want. And then my last one, I'm going to plug in. I'll just get rid of a little work here. It's a video, so if you needed that, rewind 5 seconds. But I'm going to just try some other number that's beyond 5. Doesn't matter. Try 6, try 10, try a million. But if I plug in, I'm going to do 10. -10 plus 5 over 2 times 10 minus 4. So that's -5 on the top. That's 20 minus 4 on the bottom. So -5 over 16. But it's negative, right? It's -5/16, but it's negative. And so I can answer the question, where is this less than or equal to 0? This is where I simply have to be careful with whether I include 2 and 5 in my interval. Where is it less than? Well, it's here, so that's -infinity up to 2, but it's not 0 at 2. It's not defined, so I don't include 2. But it is 0 at 5, and so when I union that, I'm going to include 5 up to infinity, and that's my interval. And we can check because they graphed this. So just for visual help here, after we've done it all, we've graphed it. Get this thing out of my way. Where is it? There. Right. So we have that discontinuity at 2. This thing right here happens right here at 2. You can see we're negative. this will just asymptotically approach that line equals 0, but it's always going to be negative in this region. And then we're positive for a brief time between 2 and 5, but we're not 0 here, so it doesn't count. And then again, we go negative. So this orange positive part is right here. And then that purple negative part again is here, right? So we can see that we've essentially gotten a pretty good idea of what this graph looks like by going through this process, and we probably could have created this from what we just figured out. All right. Let's do one more here. Let's do this one. I have x minus 3 over x plus 4 is greater than or equal to x plus 2 over x minus 5. Okay. Now, the one thing you don't want to do is try to clear these fractions by multiplying each side by x plus 4 and x minus 5, right? The reason that you don't want to do that is because if I come in here and multiply both sides by a term that has an x in it, I don't know if that's positive or negative, and that inequality, I have to account for all the possibilities. If I multiply them and they're positive, I don't have to change the inequality. But if I multiply them and they could be negative, I might have to account for the fact that they might have changed the inequality. So it's best not to do that, because then you have, in this case, you have 4 cases, and that gets ugly, right? So I don't want to do that. What I want to do is the addition principle is free, right? So I'm going to subtract this x plus 2 over x minus 5 over to the other side. And be careful with this, because I'm subtracting the entire term, right? But this turns into then x minus 3 over x plus 4 minus x plus 2 over x minus 5, and now is greater than or equal to 0. This is good. That's what I want. I want a 0. On the left-hand side, though, I want one rational expression. So how do I get that? Well, now that they're on the same side, I can multiply this term by x plus 4 over x plus 4. I don't have to worry about any signs changing here, because x plus 4 over x plus 4 is 1, and I'm just multiplying one term by it, so I'm not changing anything. The same thing happens over here. I'm going to multiply this by x minus 5 over x minus 5. There's no sign changes here. I'm guaranteed no sign change, because again, x minus 5 over x minus 5 is 1, so I'm not doing anything. I'm just rewriting stuff. But I'll have to FOIL. A lot of FOIL here. If I FOIL the first ones, I get x squared minus 3x minus 5x, and then plus 15 over, and I'm not going to FOIL the bottom. I'm just going to leave it as x minus 5 and x plus 4. But then I get minus, and if I FOIL these guys, I get x squared plus 4x plus 2x plus 8 all over that x minus 5 times x plus 4. And I'm still interested in when that's greater than or equal to 0. So I have some cleanup to do. I can rewrite this as, on the left, I can simplify that guy to x squared minus 8x plus 15 all over that same denominator, minus, and this guy cleans up to x squared plus 6x plus 8, again over that same denominator. And I got that same denominator, so now that I can combine all of this into one big fraction, one big rational expression. So again, I'm subtracting this entire term, which means the negative gets distributed through everything. So this turns into x squared minus 8x plus 15 minus x squared minus 6x and then minus 8, all over that common denominator of x minus 5, x plus 4. Still greater than or equal to 0. And I can hack and slash some stuff. Positive x squared, negative x squared cancel each other out. I've got a negative 8x and a minus 6x. That's negative 14x. And a 15 minus 8 is plus 7. Over that x minus 5, x plus 4, greater than or equal to 0. So I've simplified the original big bad ugliness down into something not as bad. This I can work with, right? Because if I find the zeros of the numerator, that's just negative 14x plus 7 equals 0, or negative 14x equals negative 7, or x equals a positive 1/2 if I divide each side by negative 7. The zeros of the denominator, those should be easy. You can just pick them out as 5 by adding 5 to both sides, and negative 4 by subtracting 4 to both sides. Right? And so I can create my number line. I have an actual real 0 at 1/2. I have a discontinuity at 5 and a discontinuity at negative 4. Right? That leaves me with 4 areas, 4 intervals that I have to check. So I just check stuff. Grab a number over here, negative 10, right? Plug it in. Negative 14 times negative 10 plus 7 over negative 10 minus 5 times negative 10 plus 4. What happens on the top? Negative 14 times negative 10 is a positive 140 plus 7. In the bottom, negative 10 times negative 5 is negative, right? Negative 10 plus 4 is negative. And that's all I really care about. This 140 plus 7 is positive. So the negative times the negative in the denominator is a positive. A positive divided by a positive is positive. I don't care how positive. I just want to know that it's positive. Pick another number between these guys. Let's say 0, because that's easy. Negative 14 times 0 is 0. That leaves me with just a 7 over 0 minus 5, which is negative 5, and 0 plus 4, which is 4. So that leaves me with a positive over a negative, or a negative. Grab a number in here. 1 is in there. Negative 14 plus 7 over 1 minus 5 is negative 4. And 1 plus 4 is 5. So I get negative over a negative, which is positive. And I'll leave it to you. Pick a number over here, 10, 100, 1,000, 6, whatever. Plug it in there. You'll see that you'll end up with a negative. So to answer this question, where is it greater than or equal to 0? That is here, but not up to negative 4. And then including 1/2 up to, but not including negative 5, right? So just remember, I cannot include my discontinuities. And so my final answer is negative infinity up to negative 4, not inclusive. And then I union that with 1/2 to 5, not including the 5, but including the 1/2. And that's our interval. All right. And here is the picture of it, just so we can see. Just scooch this up a little bit, make this bigger. But I think visualizing this makes it a little bit more, useful. We have this discontinuity at -4. That's this guy right here. We were positive to the left of it, which, yep. We were negative to the right of it, but up until 1/2. 1/2 is this 0 right here. We're negative on the left of it, positive on the right of it, and then we have another discontinuity at 5. That's this guy, and we are negative to the right of it, which, as we see, is true. All right. And I think that's it. So that's it for 4.5. And yeah, so I will see you guys next time. Next Tuesday, let me make sure I'm not lying to you. 11/24. Today is the 13th. We just did. Oh, sorry, 4/6. That was 4/6, not 4/5. We just did that. So next Monday, sorry, I forget what days I do anything on. Monday. Next Monday, we'll review for test 2. That'll actually be, let's see, actually I will be in Maine that day, so most likely it'll still be live. I'll hop on and review with you guys that day. But yeah, that's what we have. Monday is a test review, and then Wednesday, October 20th, there will not be a class or a video. You'll have that day to take your test. Thanks, and I will see you all.